Okay. Hi, everyone. Um, Welcome to the exercise class, to the second exercise class. And today is going to be, the exercise class is going to be quite dense in material. I think, so my plan for today is to first recap Fourier analysis, because I heard from a lot of you that this topic wasn't covered in the lectures before. And thus, a lot of people were struggling with the second exercise. Then I also decided to do another short recap on a Dirac delta function, which also shows up in that exercise and will probably show up later. And generally, it's a good both notions of Fourier analysis and Dirac delta are very useful to know in a way. And then I'll discuss the exercises from the second exercise sheet. And hopefully in the end, we'll still have time for some questions if any of you have any. By the way, also feel free to just interrupt me and ask questions during the exercise class. Okay, so let us start with the Fourier analysis. So let me first motivate why Fourier analysis is needed. So to motivate this, I'll just start with the simple question that we deal with maybe on daily basis or sometimes. And the question is about distinguishing sounds. So for example, how do you distinguish a guitar like playing a certain pitch from a violin playing a certain pitch? So just think about sounds, guitar versus violin. And the way instruments work is so the instrument, the string vibrates and then it creates a sound wave which reaches our ears, and then our ears are engineered to perceive these waves and hence perceive the sound. But then the music, which is the sounds, is how you describe the sound waves. And then you usually would say that, okay, I hear a certain sound, it has a certain pitch, and it has a certain volume. But then, for example, both a guitar and a violin, they can play the same pitch, but you would still be able to distinguish them. And this happens because each instrument forms a sound which is not only a pure wave, so it's not only like this usual pure sound wave at certain frequency, but it is actually a combo of many of such waves. For example, of this frequency, and also of this frequency, and so on. And this combo for each instrument, it is called timbre of an instrument, and this is a set of harmonics. And hence, the way we perceive the sound it's not only about this one pure sound wave, but more like a collection of these sound waves. And so hence, kind of our brain, which ends up distinguishing the guitar from the violin, also goes through this process of decomposing the sound that it hears into its constituent frequencies. And this is indeed the core of the meaning of the Fourier transform. So the Fourier transform just basically takes a function, in this case, in this analogy, a set of harmonics, and then it tells you exactly what are the frequencies of the harmonics which the sound wave, which the sound contains. And again, it's very useful to think about this in terms of linear algebra. So linear algebra analogy would be that, again, if we think about our harmonics or the waves of specific frequencies as a basis in the space of all possible sounds, then what Fourier transform does, it just takes an arbitrary member of this space of all possible sounds, and then it decomposes it into a set of these harmonics. So again, space of sounds, then we have a basis, which are these harmonics of particular frequencies. And then we just have a decomposition. Okay, so let us now start with like more formal mathematical description, and we will start with, so this was motivation, then we start with Fourier series, which is a discrete case, and I think it's easier to start here. So suppose that you're given a function f, which has a period 1, and it's, as we say, it's reasonably nice. So I'm not going into, so this is not a mathematical course, I'm not going into like all conditions that f has to be. Let's say like it's continuous, yeah, it's smooth, and generally, because we're talking more about physics here, in physics, we just usually assume that almost all functions that we're trying to analyze are reasonably nice. So they're smooth, they're continuous, differentiable, and so on. And for this function, we can write it out as a sum of harmonics. So the sum of sines and cosines. Let's see, let me start with a sine. Like this, where n is just summed over all natural numbers and negative numbers. So, okay, so here, the subtlety, like why we both have sine and cosine, where, well, there is this is very easily kind of explainable by saying that, okay, sine is an odd function and cosine is an even function, and we have no guarantee that the function f that they're trying to represent is exactly odd or exactly even. So in the end, like for an arbitrary f with this period 1, we have to represent it as a linear combination of both even and odd functions, even and odd harmonics. So this is a bit of a bulky representation. So let us use the representation of sine and cosine in the complex plane with the complex exponential, and let us rewrite it in terms of e to the power 2 pi I alpha. Yeah, I'll do it explicitly, since it also can be a good reminder of like how you deal with the complex exponential numbers. So like then we can write that f of x, the summation remains. We write out sine as e to the power I 2 pi n x minus e to the power minus I 2 pi n x over 2i plus, and then we write cosine in terms of complex exponential as well. x plus this over 2. Then we regroup, and what we get is the following: 2n plus bn over 2 plus n over 2 minus an over 2i. Okay, and here we do the trick for the second component of the sum. We just let's say we just separate it into two separate sums, and for the second sum, we just substitute n with minus n, and then what we get is the following sum: e to the power I 2p n x, and here we have one big argument. Plus. And we call this coefficient Cn, and hence we arrive to the following representation, that f of x is equal to Cn e to the power I 2 pi nx. And this is called Fourier series of f. And Cn are called Fourier coefficients. Of course, the coefficients themselves, they depend on the function f that we're trying to decompose in terms of this series. And so usually, Cn actually depends on f, and usually like in mathematics, you would write them as f hat of n. So again, maybe if there is any confusion about the hat, so this is f of n is not the operator, this hat is just a mathematical symbol. Actually, maybe not to confuse people, then I would just substitute with the wave, with the tilde. Okay, and the question now is, so we have this decomposition. How do we find out the Fourier coefficients f tilde of n for a given function f of x? Well, what we can do is let us integrate from both sides from 0 to 1 f of x with the added component e to the power minus I 2 pi kx dx, and then here we can also integrate n e to the power I 2 pi x n minus k dx, and this is the sum here, still stays. And here, to solve this, we actually need a following fact, which is very easy to solve, which is very easy to prove, that the integral from 0 to 1 e to the power I 2 pi x n minus k dx is equal to 1 if n equals k, and 0 if n does not equal k. So essentially from this integral, from this sum, the only integral that survives is the one where n equals k. So then what we get is this f tilde of k. And hence we have our equation, which allows us to find the Fourier coefficients for this for the function f. So let me just write it again. Integral 0 to 1 f of x e to the power minus 2p nx dx. So this like doing this also is called like inverse Fourier transform. Okay, so we know how to find the coefficients, and again, there is a certain mass subtlety here, which again points out that this always will only work for reasonably nice functions f. So here what we do mathematically is actually in this step, in the first step, we interchange the sum, we switch the sum and the integral. And the sum is not finite, it goes over, it goes from minus infinity to plus infinity values of n. And this essentially, and switching this infinite sum with an integral, it doesn't work for every function, it works only for nice functions. But again, just to remind you, we're only working in physics with nice functions. So let us not kind of bother ourselves with this too much. Okay. So again, I will highlight here that as in before, we already had this intuition that this is very similar to the way we think in linear algebra. So, and here the analogy is as, so we consider the space F, the big F space, which is a space of this nice functions of period 1. And what we do, we essentially, we expand it, and what we do in Fourier series, we expand F in the basis of functions e to the en of x, which are the functions of this complex exponential e to the power I 2 pi n x. And as we've seen just before here, actually this is not only a complete basis for this kind of space, but it's also an orthonormal basis. Why is it an orthonormal basis? Because exactly of this integral here, which you can, we can just quickly take it as an exercise like afterwards. And and here, just to remind you also that orthogonality is usually something that is defined with respect to the particular inner product of the space. So for the space of the functions of this continuous functions, the inner product that is usually considered is just the integrand of the the considered two functions of which you want to compute the inner product of, on the interval on which these functions are considered. So, and hence, again, we have this linear algebra analogy that we have a particular space of functions, and then we're trying to decompose it with respect to this basis of this complex exponentials. And the mathematical fact is that you can always do it for this space of nice functions. Okay, so now we have the next question to answer. So we were only talking about this particular type of functions which have a period 1. What about all other functions, you might ask? What about just functions f, which go from R to C, which might not be periodic? So can we do the same thing with them? And the answer is yes, you can. So, and the intuitive way to understand this idea is that, okay, so previously we had these functions with period 1, which we know how to decompose in terms of this harmonics. Okay, now we go a step further and we say that, okay, let us consider functions f k from R to C with periods pk, So the functions with period 1 we can decompose in terms of the basis elements e to the power 2 pi I and x. If you have a function with a period pk, then you can just kind of scale this function so that it would just have a period, would be periodic with period 1. So for that, you just need to scale it with the factor pk. And then you can just, if you scale it in that way, then you can also write it as a Fourier series of the following basis. So in following basis, so e to the power 2 pi I n over pkx. So this is just like we scaled it so it would have a period 1. Okay, and what if, and now let us consider what happens if the function f is not periodic. What we can do, we can extrapolate this function as a limit of these periodic functions of these periodic functions fk with periods pk, the periods of which would get larger and larger. So in limits of pk going to infinity. And then the intuition is that if you take the sequence of these functions fk, then for each function, we would just write it as like a decomposition in this basis. And then as pk's would become larger and larger, we obtain a sum of exponentials which are evaluated on more and more densely packed points. And essentially in the end, when we kind of arrive to the function f itself that we want to represent, which we can view as a function which has a period of infinity, this sum in this continuous limit just turns into integral. And hence we can just, so as pk goes to infinity. And hence we can just represent f of x as an integral over r tilde of psi e to the power I 2 pi psi x d psi. And again, as in the Fourier series, we have here the question again, how do we find this function f tilde of psi given the function f? Yeah, so this process is called Fourier transform. And here we can note what was the way that we obtained the coefficients for the Fourier series just 2 pages before this. So for the Fourier series, we obtained the coefficients as the following integral. And this gives us an intuition of why we can also write this Fourier transform of the function f as a similar integral. And this is called inverse Fourier transform. Okay. Yeah, so I will not, again, I will not say which functions f exactly satisfy the, satisfy that the fact that they can be Fourier transformed, just keep in mind that, for example, like it's good if the function is continuous and it's yeah, the function is continuous and it's also bounded, then probably it has a Fourier transform. It can be Fourier transform. Okay, so an example. Yeah, another thing to remember, which is a property that one can also prove in, like, if you go through a mathematical proof of it, is that, like, for example, if you have a function f of x, right? Then you can write its Fourier transform 2 pi. Sorry. Then you can write how can we express f tilde by f of x. And if yeah, and essentially this just means that if we apply the Fourier transform to the function f and get f tilde, and then if we apply the inverse of Fourier transform, which is this one, to the function f tilde, to that, then we get function f back. Okay, which would be useful for when we will be considering the delta function a bit later. So examples, maybe, yeah, I just took them from the mathematical textbook, but maybe if somebody is interested in, like, trying out the Fourier transform for some functions, then they can just take these functions and see what happens. So for a function f of x, which is this one, like, the Fourier transform would be this function of x, which is, for example, this one. It would be, I think it's sine. And then there is this peculiar function, which is the Fourier transform of itself. And maybe some concluding remarks are the following. So sometimes you wouldn't see this coefficient, you wouldn't see this coefficient 2 pi in the definition of the Fourier transform. So of course you can omit this 2 pi in the argument of the exponential. However, that would result in the factor 1 over 2 pi here, square root of 2 pi here, just to have this kind of symmetric property of doing Fourier transform both ways. Yeah, another remark is that, again, like, the physical motivation for this is mostly as something that allows you to decompose a given function in this particular basis of harmonics. And this is useful, for example, in signal processing, like the same signal processing, even the signal processing as we do one of the sounds in our mind, like the sounds of violin or guitar. But also in the sound processing, in machine systems where you just have an arbitrary function, and then it's always useful. It's always useful to decompose it in terms of harmonics, because harmonics are the objects which are much easier to work with than an arbitrary function. And then you can see, okay, this harmonic, you can see the profile of the Fourier transform of the particular function, and you see, okay, so this profile shows me that this frequency is more present than that frequency, and so on. Yeah, okay. So before I continue with the delta function, are there any questions about the Fourier transform? Okay. Was there a question? Yeah, I see a question. Ah, okay. Shouldn't the first sum with just sines and cosines only go over naturals instead of integers? You can write it as a sum over you can write it as a sum over naturals as well. You just have to, like, if you take into account that like sine and cosine are odd and even function. Like, in a sense, you can write it as, if we only restrict it to the natural numbers, yeah, possibly 0, yeah. Then you can just write it as an plus a minus a minus n sine 2 pi n x plus bn plus b minus n cosine 2 pi n x. And then you can label this as nu n and nu bn. Okay, good. Okay, now the next small recap is about delta function. So I talked a bit about it before, but I think kind of structurizing this knowledge wouldn't hurt. So it would be surprising to hear, but the motivation for the delta function, which is a very mathematical, very idealistic object, but the motivation for it is actually physical. And it were actually physicists who first used this function, and actually from the usage of this function, the function analysis, partially from the usage of this function, or because of the fact that physicists needed this function to operate it with, the function analysis was born in the 20th century. And like to understand the intuition behind the delta function is that you can do it in the following way. So for example, suppose you have a function f of x, which is defined for all values x in R and is finite everywhere. And what we want to have is we want a filter which singles out its value at the particular point x0. The value of f at x0 in R. And the idea is that delta function is exactly this filter. To understand how this filter works, let us first work with a discrete example. And for the discrete example, suppose that we have a sequence A1, A2, and so on. So it's just AJs where J is 1, 2, so on. And we want to kind of select, we want to point out a particular AI. And the way we do it is that we apply a certain selector, which is called a Kronecker delta, and sum over all numbers applying this selector. So we use delta ij. So delta ij is this object, which is 1 if I equals j, and 0 if I is not equal to j. And then if we look at the sum over j's, delta ij aj, then essentially the component of the sum is non-zero only if and only if I is equal to j. So the only component that survives is ai. So this is called Kronecker delta. And this delta, it also satisfies two properties: that it's normalized because the sum over all j's, delta ij, equals 1 for all i's, because again, only one component of this sum survives. And so this is a normalization condition. And also it's symmetric. So delta ij is equal to delta ji. For all, yeah. So this is symmetry. And now we want to introduce something similar, but in the continuous case. Again, to single out a particular a particular component, but on the continuous arrow of numbers. And for that, we just have to substitute essentially the summation over the elements or with the integral over x's in R. And then the specified index I would be substituted by a particular point x0 that we want to select. And then the function that kind of represents our desires would look the following way. So if we sum over a function f of x with this object, then we single out its value at point x0. And this is exactly how, and this object is called the delta function. Okay. So there are many ways how to come to the delta function, just looking at the limit of particular sequences of functions. So I'll just show you one way, and I'm sure you can come up with like 10 or 100 other ways or other functions which do the same, but I'll just show you how it's done, and I hope that will also give you some physical motivation. So suppose that we have a function of like f of x here, and then we want to find a function which singles out its value at x0 if we kind of integrate with this function over the function f. Okay, and for this we take as a preliminary object, we take this kind of window function here, which is just like as a step function, looks as a step function, but it goes from x0 minus epsilon to x0 plus epsilon, and its height also depends on this epsilon that we choose. But for now, we just choose this particular epsilon, and we look at this window, and then we integrate the function f like over this window, So then, so this window function, let's call w of x, would then be 1 over 2 epsilon if x is between x minus epsilon, x plus epsilon, and 0 otherwise. Okay, now we want to look at what happens if we integrate f of x together with w of x dx. So w of x only, its domain is only from x0 minus epsilon. So non-zero domain is only from x minus x0 minus epsilon to x0 plus epsilon. So then we only run integral from this point to this point. Then we have f of x dx. Okay, let us call the integrand of the function f as a big F. So then we arrive to f of x0 plus epsilon minus f of x0 minus epsilon over 2 epsilons. And it's easy to see that, like, actually this is exactly the definition of the function f at point x0 if we take the limit of epsilon going to 0. Because if we take this construction here, this is actually how the derivative of f at x0 is defined, and this is exactly the value of the function f at point x0. Okay, so the idea here is that kind of the more narrow you make this, we make this window function narrower and narrower. So sorry, it will only also go like this. It will, like, its height will grow and grow of this window function, but it will become narrower and narrower. And in the limit of epsilon going to 0, this window function can be seen as something that approximates the delta function, because it in the limit of epsilon going to 0, it acts on the function f in this integral exactly in the way we expect the delta function to act. However, the delta function cannot be defined as just like being this function, because this, as you can see, that this function w of x would be ill-defined in a case of epsilon equals 0, because it would just be infinity at point x0. This is not like a good definition, but it's a good it's a good way to get an idea how delta function can be approximated. And this also, so this does give an intuition, but it's not, but say v of x is not well defined when epsilon goes to 0. Which also gives us actually, so this kind of fallacy also gives us the intuition that of thinking about delta function as not a function of x, but rather as something that acts on a function f of x. So it's kind of delta x minus x 0 acts on f of x. And as I mentioned before, if you come to solving this problem like more rigorously, more mathematically, then you would actually just say that delta lives in completely other space of functions, which just act on the space of functions where the function f of x lives. But we can also just think about it, just think about delta function as something that only only makes sense if it's put in the integral, and then the value of the integral then depends on the function f of x on which we're acting with, so this delta function. Okay, so the properties of a delta function is similar to the Kronecker delta. The integral is equal to 1, so it's normalized. Then also delta of x minus x0 equals delta of x0 minus x. So it's symmetrical. And then some other properties include x delta of x equals 0, to prime of minus x minus delta prime of x, x delta prime of x minus delta of x. And something important, this property is important, it's about scaling. So if you try to scale the delta function, then it scales the following way. So not as you would expect, as just taking the coefficient alpha out. And finally, the Fourier transform. So if we take Fourier transform of the delta function, y delta of x dx. So here is just the function delta of x acting on this complex exponential. And hence, it just tells us the value of the complex exponential at x equals 0. Which is this, so it'll be 1. And this also tells us that actually, that the inverse of this, so kind of the inverse of Fourier transform of the identity of the 1 would actually give us exactly the delta function. So this is also another way to represent the delta function. Okay, and finally coming to the physical meaning of the delta function. As already mentioned in the beginning, it actually stemmed from like physical applications. So one of the most evident like fields of application is, for example, the electrodynamics. So in electrodynamics, what we do, sorry, there is a question. Okay. So the question is, the problem here is that this holds for any constant on the exponent, not just 2 pi. Okay, this comes back to, this is not true. This comes back to me, to this comment that I made here. So the Fourier transform is defined up to this, up to this factor here. Like the way you can in principle put any number instead of 2 pi. You can put any number, but the number that you put here would influence the kind of the coefficient that would end up here. So like you can in principle do the Fourier transform not only with 2 pi, but like just random alpha. But then this would result in you having these coefficients here. So essentially for each coefficient alpha that you put in the argument of the exponential, you would need to slightly scale your Fourier transform. So you would need to a bit like redefine what you mean by a Fourier transform. Yeah, so for example, like if you don't do 2 pi here, then you have to do 1 over square root of 2 pi here. And then you would end up not with the 1, but 1 over square root of 2 pi. And the same would be with the inverse here. Does it make sense? Okay. So coming back to the physical meaning, to electrodynamics. So electrodynamics, the very common idealization that physicists use. Oh yeah, I didn't formulate what we do in electrodynamics. So in electrodynamics, the common problem that we have a certain distribution of the charge in the space, which we denote as rho of r. So you can just think about it as a lot of charges in a big volume, which are somehow distributed. And the common problem is to find out how the potential looks like in this area. Sorry. And for this, you need to solve like a certain equation, which depends on this charge density in this area. However, in electrodynamics, there is a very common idealization, which is called a point charge. And the point charge, it's like Q at point R0. And it is an idealization of a finite sized charge in zero volume. And sometimes we need to find, for example, to solve what is the potential created by such a charge. We need to be able to write down the way to mathematically write down the density charge for this point charge, and this is exactly where the delta function comes in. So then you just write the density of the charge as Q delta function of R minus R0. So this was in electrodynamics. The same can be done, for example, in gravity, where we have where we can have a certain idealization, which is like a point mass. And and historically, delta function was first introduced to work with equations in electrodynamics, and then so this was in the end of the 19th century, and then in the beginning of the 20th century, Dirac created a more complete theory of these delta functions, and then this work started this whole idea of function analysis and this more mathematically rigorous approach to looking at functions like delta function. Okay, so this was a bit on the delta function. I think the important parts to remember is that physically delta function corresponds to point charge or point mass, or just point excitation of a certain value. And the important properties to remember are its Fourier transform, and maybe it's some properties of its derivative. Yeah, that's its symmetric, and how it scales. Okay, now let us we finally came to the, by the way, do you want a break? If you need a break, you can just tell me in the chat. Okay, it doesn't seem that, it seems like nobody's writing, so I guess I'll just continue. Fine. So now let's come to the exercise sheet. Okay, and there are 3 exercises in the exercise sheet. And so the first exercise is about controlled gates. The second exercise is about some operators and unitaries in trapped ions. And the third exercise is about Mach-Zehnder interferometer. So let's start with the control gates. I think you already heard about them a bit during the lecture, but maybe I'll remind you, since it never hurts to remind. So control gates are usually gates on 2 qubits. It can be gates on more than 2 qubits, but we just consider gates on 2 qubits. And the idea of the control gate is that that it performs an operation which changes the state of the second qubit based on the state of the first qubit. So an example of the controlled gate, which is most widely used, is a CNOT gate. And the idea is the following. So if we do a circuit and we label the first qubit A and the second qubit B, and we suppose that they're initialized in states, both in state 0, and then we apply a CNOT gate. Yeah, maybe a small interlude before I continue further. So like this, the gates that you see here, this two qubit gates, also 1 qubit gates, they can be drawn in this way to form a circuit. And you'll probably see quite a lot of these circuits during the semester. And I would really recommend you to kind of to sit down and maybe analyze a couple of circuits that you will encounter during the course. Because first, that's going to be one of the exam questions, most probably. And secondly, it takes some time to be able to read these circuits like easily in a more relaxed way. So the idea is that each line corresponds to 1 qubit, and the circuit is read from left to right, and the sequence of gates is applied from left to right. And the circuits are a very good way to represent how quantum algorithms work in general. So, but let's come back to our CNOT gate. So this is a very simple component of the circuit. And the way it works is that, like, if both of the qubits are in state 0, so the first qubit is in state 0, then the second qubit doesn't change its state. However, if we are in a different situation where the first qubit in a state 1 and the second qubit is in a state 0, and we apply the CNOT gate, then the first qubit doesn't change its state, but the second qubit flips. And the idea of the CNOT gate is exactly this. Like, if the first qubit is in state 0, then nothing happens to the second qubit. If the first qubit is in the state 1, then the state of the second qubit flips. And this flip operation, as you might have seen from the previous exercise sheet, corresponds to the X gate, which has the following matrix representation in the 0-1 basis. And hence, CNOT gate is sometimes called controlled X gate. And we can write very easily what is the action of this gate in terms of brackets. So as I said, if the first qubit is in state 0, nothing happens. So if it's in a 0 state, then we apply identity on the state of the qubit of state of the second qubit. If it's in the 1 state, then we flip the state of the qubit of the second qubit. So we apply operation X on qubit B. And just as an exercise, we can also write it out in how it looks in terms of the matrix in the 0, 1 basis. So 0, 0 would correspond to this matrix. Tensor product with the identity. So this is on A, this is on B, plus this is on A, plus tensor product, the flip on B. And now we just have to calculate the tensor products. So if we multiply two 2 by 2 matrices with the tensor product, then what we get is 4 by 4 matrix. And the way we multiply is, like, first we take this element here, and then we take this element and multiply it with this matrix. We get is just 1, 0, 0, 1. Then we take the 0 element and then multiply it with the same matrix. Obviously everything is 0. Then we take this element, also multiply it, so get zeros, and finally this element, also multiply it with this matrix, and we also get 0. It's x on AB. Thus, here we do the same. So we take 0, multiplied by this matrix. 0, 1, 1, 0. Yeah, I'm drawing the dashed lines, so just it would be more representable, but usually, like, you don't draw dashed lines in the matrix. You take, so first we already took this one, then we take this one. Sorry, the first one of course gave us 0 because we multiplied by zeros. So the second one also gives us zeros. Then the third one also gives us zeros. And the fourth one finally gives us non-zeros because we just multiply every element of this B matrix by 1. Okay, good. Then this is just summation. Then what we get is so this is a matrix of the C0 gate. In this exercise, you would also encounter the following gate, which is CZ gate. Let me start on the another page. So CZ gate. So CZ gate is controlled Z gate. And again, as we draw it, this is A and B. So the same as C0 gate was a controlled X gate, CZ gate is a controlled Z gate. So instead of the flip operation, we apply the Z gate. So Z gate, just to remind you, is this one. So it just gives a phase of -1 if the state of the qubit is 1. Okay, and then analogously, we can just write CZ in terms of brackets, which is, again, if A is in state 0, then we don't do anything on B. If A is in state 1, then we apply the Z on B. And I'll just write it as a tensor product of the matrices, the same as we just did before. And now I will not do like that process that I did before, but just write the result. And Okay. So yeah, and in this exercise, you'll just have to first prove some identities about the controlled Z gate, and then decompose the controlled Z gate into two Hadamard gates and a CNOT gate. And you can do it just by like guessing in which order they have to be next to each other. And there are not so many options, so that's fairly simple. Okay, so this was the bit on the controlled gates. Is it clear for everyone how to do the tensor product? Yeah, there is a question. Yes. Yes, I can show how this can be done in terms of for the CNOT matrix. So again, the CNOT matrix looks the following way. Maybe I should have done it bigger, but just like this. Yeah. Like an easy way to see how the matrix can be written written out in terms of brackets, like in case 0, 0 and 1s for A and B, then is to kind of label its columns and its rows. So, and the way we label them here is like we start with 0 on A, 0 on B, 0 on A, 1 on B, 1 on A, 0 on B, and 1 on A, 1 on B. So this were for the columns. And now for the rows, we do the same in the same order. And then we can look at which components are non-zero and which intersections they are. So we have here, 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 and here. So the first one is like this one. Maybe I do it this way. So okay, it's too big. So the first one is here. And it's at the intersection of 0, 0, yeah, and 0, 0 here. So we can just write it as 1 by 0A, 0B, 0A, 0B. Plus the second one is an intersection of 0, 1 and 0, 1. So again, we can write it as plus. So the third one, by which I mean this one, is an intersection of the row 1, 0 and the column. Oh, sorry. Actually, yeah, I looked at the wrong place. So it's this intersection of the row 1, 1 and the column 1, 0. And finally, the last one, which is in the fourth column, is an intersection of row 1, 0 and column 1, 1. And in this way, we can write out the matrix in terms of brackets. Okay, there is another question. Ah, yes, it's already answered. Thanks. X, Y, tensor Z, V. Yes, exactly. This is correct. Yes. Okay. So now the second exercise is about gates and trapped ions. And I have a small, first I have a small comment about this exercise. So you don't have to do the parts C and D. So it's only, yeah, actually remove them from the new version of the exercise sheet, which is now in Moodle, because I think because when I started solving them myself, then I found out that they're the techniques that you have to use there are not as simple, might not be that simple, and so I decided to remove them. So you only need to do A and B. Okay, so here we get kind of a physical example of trapped ions, which are used in quantum computing as qubits. And we look at some processes which happen in trapped ions. So generally, to describe the physical processes and the way the qubits are operated in trapped ions is to consider an ion as a combination of two systems which represent internal and external degrees of freedom. And yes, because it's two systems and we're working in the framework of quantum mechanics, we know that the combination of these two systems is described by a tensor product of their Hilbert spaces. And the internal degrees of freedom are two-level systems, qubits, with the basis 0, 1. And the external degrees of freedom are like this motional degrees of freedom, for example. And they have a basis with which is labeled by natural numbers. And there is like this infinite number of these motional degrees of freedom. So, and then different different transitions can happen in this ions. For example, this transition can happen only within internal degrees of freedom, or it can happen so that it couples internal and external degrees of freedom in a sense that, for example, we change the state of the qubit and we also change the state of the motional degree of freedom. And to describe these processes, there are certain operators that are introduced, which are called raising and lowering operators. And raising and lowering operators are just these operators which denote an operation of going from one basis state to another, to the next one. So for example, for the qubit, for the internal degrees of freedom, we label them as sigma, dagger, and sigma dagger acts on 0, and it yields 1, state 1. So this is a kind of a raising operator. And just sigma, it acts on 1 and yields 0. So this is a lowering operator. And these operators, you will see them throughout the course. Also, if you do things like, for example, harmonic oscillator, or if you take courses such as statistical physics, and so then you will, or quantum field theory, then you will see kind of these operators a lot. And the same as for the qubit, you can also introduce this raising and lowering operators for the motional degrees of freedom, or the external degrees of freedom, which we label as A dagger, which acts on n. We also have to include this normalizing factor. This, and the lowering operator, just again raising, and the lowering operator just lowers the state in the previous one. Yeah, since I took away the C and D parts of the exercise, then you don't need to bother yourself with like this raising and lowering operators for the external degrees of freedom, but you have to work with the operators, the raising and lowering operators for the qubit. And yeah, there is, so in this exercise, you have to look at the operation R, which depends on theta and phi, some parameters, and which is written out as exponential, as a following exponential with these operators. And this is a good exercise to kind of look at this technique of having of what you should do if you have a certain operator in your in the exponential. Like then, yeah. So just from the first glance, it's not clear what to do in order to apply this operator to some state. And for this, you just to find out how exactly this operator R of theta and phi looks like and what it does to the internal degrees of freedom, to the qubit. We need to write it out in the matrix form. So for this, we need to write the raising and lowering operators in the matrix form in 0-1 basis. So we can write them the following way. So the lowering operator would just be 0-1. And the raising operator 1-0. And then we can write this as an exponential of a matrix. So we have here is phi plus minus e phi. Okay. And we arrive to the following: exponential of I theta over 2, 0. Let us note the following, that the matrix that we have there in the exponential is can be written as this. Sorry, so if we take this matrix and multiply it by itself, then we get the identity. Okay. Great. So this is kind of very good matrix for the purposes that we want to do. So then let us continue with the following interlude. Up to we noted that this matrix squared gives us the identity. Let us take an arbitrary matrix A and look at its exponential. So e to the power alpha A. So A is, like, say, n by n matrix. Then the matrix exponential is defined as just a Taylor series. So it's the sum from 0 to infinity, I alpha to the power n factorial a to the power n. But here we have matrix A, which squared gives us the identity. Then I will not prove it here, but just in case I included the proof into the solutions. But for this case, you can see that since a squared equals identity, then we can just separate this Taylor series into the Taylor series for the odd ends and even ends. And for the odd ends, because a squared is identity, then we would only be left with the 1a. And for the even sum, for the even Taylor series, then we would get, because a squared is 1, just identity. And hence, for the matrices which satisfy this condition, we can write out that the exponential is just this. And yeah, just prove it's an exercise. And hence, if we have this matrix, we can write it out as and this is how you get how the R of theta phi looks like. And then you'll see to which it to what operations it corresponds. Just also try to think about the block sphere and what it does for the block sphere. So yeah, in the second part of the exercise, you'll need to find the values of theta and phi for a particular like for a particular operation, like for example for a bit flip. So which values of theta and phi would correspond to a bit flip? Okay. And then finally, the last exercise is about Mach-Zehnder interferometer. Okay, so Mach-Zehnder interferometer, to understand it, so it essentially is a device which at which we can point the laser, and then just measure the intensities of the laser beams which come out of this device. Like, how is this device built? So the founding element of this device is a beam splitter. So yeah, let me draw it with some color. Let's say orange. So this is a beam splitter, and we shine the beam splitter with some laser beam or photon, and then the beam splitter, with some probability, it reflects the beam, and some part of the beam just goes through. And the idea is that you can see the beam splitter as just a quantum gate. So for the purposes of this exercise, I labeled the transmitted and the reflected beams as T and R, but you can also just understand them as 0, 1 states of the beam. And the idea to see the beam splitter as a gate is that it performs the following operation. So if the incoming beam is in a state T, then it transforms it in this state. And then if it's in incoming state R, then it transforms it in this state. So this can be represented as a quantum gate. And the Mach-Zehnder interferometer essentially has two beam splitters, one after the other. So sorry. So we have the incoming beam, which is then separated here and here, and goes here. So here we have some mirror. It's an experimental setup. And here we have two detectors. So if we label this gate as B, for example, and here we have the measurements, then actually the way this interferometer is built is the same as the following circuit. So we have a qubit in a state psi. Then we apply the gate corresponding to the first beam splitter. Then don't mind the mirrors. The mirrors are just there to put one beam splitter after the other. Then we have a second beam splitter. And then we have the measurements in the computational basis. So this TR basis. Okay, and what you have to do is just to find out how does the quantum gate which corresponds to the beam splitter look like, and then some measurement, and then some measurement probabilities, and then after there is a modification for which usually the Mach-Zehnder interferometer is used. So what we do is we introduce a phase shifter on one of the legs. Actually, I don't remember which leg it is in the exercise, but let's suppose here. So this is a phase shifter. Let's call it S. And the phase shifter S is just, it just acts on one of the states and doesn't act on the other. So if it acts on the state T, then it gives you a phase. If it acts on R, then it doesn't give you anything, any phase. So essentially what the phase shifter does, it accumulates the difference in the phases between two legs of the interferometer. And again, as in quantum circuit analogy, this phase shifter would just be in between these two beam splitters. So again, measurement. And of course, since it shifts the phase of one one basis state with regard relative to another, then of course this would influence the results of the measurement. So the question is there a physical reason why we're measuring T and R and not 0, 1? So, okay, so this is not a physical reason. This is just labeling. This is just for labeling purposes. Like you can just say that T is the same as 0 and R is 1. So again, maybe to highlight this, since I feel like there is a lot of confusion about this. So the things that we put inside the Ketzen bras, they're not the physical quantities. Like it's just the labels that we choose for certain physical quantities. So it's the same as like, so we have this abstract two-level system, and then we choose to label one of the levels as 0 and one of the levels as 1. I can also label them as happy smiley and sad smiley, and then, yeah, then it would be like this. This is also totally acceptable. It's not very, so this is 0, for example, this is 1. Yes, the whole idea of two-level system is very abstract. Like in the real practical setting, these two levels would correspond to levels of particular energy in a particular molecule, between which the transitions can happen. But we still choose to label them as 0 and 1. Anyway, so in the end, you introduce this phase shifter in between two beam splitters, and then this, of course, influences your the probabilities with the respective probabilities with which you get different measurement results. Okay, I think. Oh, I'm even on time. Okay, good. I think I'm done with my plan for today. Are there any questions? Okay, so now the questions about the exercise sheet 1. So the question is, isn't the normalization condition that AA equal 1? Because PP lead to infinity in A for me. So, okay, so back to my discussion on the Kronecker delta and so on. So, like in the discrete case, when you have a basis of AIs, let's say, then the condition that you have to use is that AJ AI equals delta IJ. This is a discrete case. However, we just saw, sometimes the bases are not discrete, but they're continuous. Like the same way as we go from Fourier series to Fourier transform. So when we go to the continuous case, where, like for example, for P, then we also have to shift from the delta ij, like a Kronecker delta, to a Dirac delta function. So then the condition that we would be looking at would be the following. Like in the second exercise, if you compute like this inner product between P and Q, then you would get actually the delta function. And Z. Sorry. So that was a typo, like coming from the first version of the exercise sheet. It's so like in the on the Moodle it should be it shouldn't be there. So let me know if it's still there. So like first it was like this, so this is not correct. Like what it should be is the integral over P in R. Okay. If there are no more questions, okay. Upload the notes from tutorial to Moodle. Yes, I can do that. Yeah, if there are no more questions, then you can always email me. So if it's regarding the exercise sheet, it's always more useful to email me than Lídia because I'm the one who's mostly doing them. And yeah, you're always welcome to come to the question and answer hours on Tuesday, and we're also in the Zoom meeting at that time, so you can also just ring us on Zoom. It's also fine. Okay, cool. Then have a good rest of the week. Thank you. Yes, I'll notify you if I update some part of the assignment. Okay, perfect. Bye.